Good afternoon. Today we will start the topical revision for Chapter 1 Information Representation for AS level and code 9618. Okay, so let's see how we will solve some past paper question for Chapter 1. Right? Okay, the first question is that you have to convert a binary number into the hexadecimal. Okay, now you can see here there are 8 bits for the binary number, and you have to convert them into hexadecimal. So remember the key: whenever you are asked to convert into hexadecimal, you have to make two groups. One group is for 4 bits, and the second group is also for 4 bits. Okay, so and you have to move from your right side to left side to make two groups. Okay, now my first group, I have underlined it with red color. This is my first group, and this one is the second group. Okay, so what you have to do, you just need to memorize this table. Okay, up till here 1 2 4 and 8. Okay, this half table, and remember this power, they will be it will be very easy for you to solve these kind of questions. So for 1 0 0 0, what you have to do is simply that you can write this number over here, 1 0 0 0. Okay, under this table, and then just add the powers for those whose bit is 1, right? For 1, I have the power of 8. Okay, so what is the equivalent value for this group? I have equivalent value of 8, right? So I can write here 8. And for the second group, 1101, again I can write it over here. This is 1011. And what I told you, you have to add the numbers whose bits are 1. Okay, so for 1 the power is 1, for 1 the power is 2, for 0 I will not add this because it's 0, 0 mean nothing, and then for 1 I will add the power 8. Okay, so 8 plus 2 plus 1, 8 9 10, and this is equals to 11. Okay, so I'm writing here 11, but because the question is that you have to convert it into hexadecimal, so remember what you have to do, that you have to write the equivalent value for 10. Now remember, for A we have equivalent value of 10, for B it's 11. Okay, for B it's 11, for C it's 12, for D it's 13, for E it's 14, and for F it's 15. Okay, so according to this table, the value for 11 will be replaced by the letter B. Okay, so my final answer here, it will be B11. Okay, so I will be writing equals to B, sorry, B, not B11, it's B8. Okay. Okay, coming to the next question. Convert the following binary number into BCD format. Now, if you remember what is BCD, BCD stand for binary coded decimal, where each digit is treated as a separate binary number, and you have to write the equivalent value of each digit into 4 bits of binary. For 9, you have to convert the 9 in using binary conversion, so you have to write the equivalent value for 9. So according to this table, if I consider this table 1 2 4 8, why only I'm considering 4 bits? Because each BCD digit is represented by a 4-bit binary digit. Okay, so for 9, if I will add 8 plus 1, these powers, so I will get 9. Okay, so my equivalent code for 9 can be 1 0 0 and 1. Okay, and then again separately I will write the 4-bit number for 7. Okay, for 7, if I add 4 2 and 3, 4 2 and 1, so I will get 7, 4 5 6 and 7. So I will not write any bit under 8 because it will not be adding up. Okay, so for getting 7 I need 0 for this bit 8. Okay, and 4 2 and 1 will be on, so I will get 1 1 and 1. Okay, so this is equivalent value for 7. Okay, and this is equivalent value for 9, so this is the equivalent of BCD. Next question is, using 2's complement, show how the Denny number could be stored in 8-bit register. Okay, you have been given an area of 8-bit register, and the value is 114, and you have to use 2's complement to convert the Denny number into binary. Okay, now here see, this is a positive number, right? For positive number, you just need to convert it into its equivalent binary number. one is the direct method and the other is the indirect method. The one is a long method. So first I will use the direct method, where you can just write the powers over here: 1 2 4 8 16 32 64. What is going on? Okay, for the next question, you have to convert binary value into its equivalent binary number using the 2's complement. Now, look here, this is the positive number and this one is a negative number. Okay, so negative numbers can be represented by using the 2's complement. So we'll see how you will convert into 2's complement. But here you can see this is a positive number. So for positive number, you can use two methods. One is a long one and the other is a short one. In the short one, what you have to do, just you need to memorize these powers in this order and just write them on the top of your box, okay, that is given to you. This is a 8-bit box, so I will be writing powers till 128, okay, and then I will see which number I will add or turn on the bits 1, so that I can get 114, okay. So if I do that, if I write here 0 and if I do different combination, how can I get 114? 64 plus 32 plus 16, okay, plus uh, 1 and 0, okay. Now see, if I add 16 plus 32 plus 64 plus 2, I will get the number 114. So this is something, that you have to do mental mathematics over here to add up different numbers so that you can get 114, okay. So other method you can use is that you just need to convert it into binary by dividing this number, the binary number, with 2, okay. Why 2? Because we want to answer in binary number. So I will be using this formula. So I will get 2 5 times 10 and 1 2 7 14. Okay, 57 times 2 is 114 and I get the remainder 0. So whatever remainder I'm getting, I will write over here, okay. So again, I will divide it with 2. So I get this number. So 28 times 2 is 56 and remainder is 1, okay. So keep on dividing. 2 times 14 is 28 and I get the remainder 0, okay. And again 2 times 7 and remainder 0, okay. And 2 times 3, remainder is 1, and again it is divisible 2 times 1 and the remainder is 1, okay. Now see, I got here 1. 2 times 1 is 2 and remainder is 1. So now this 1 is smaller than 2, so it cannot be divisible by 2, okay. Now you have to write the answer, and when you are writing the answer, remember you have to follow this direction, okay, and from here, and you have to include this 1 also, okay. Don't forget to write it in your answer. This you have to include in your answer, okay. Okay. And now see how many bits you have. 1, 2, 3, 4, 5, 6, 7. 7 bits, okay. And how many bits you want? You want 8 bits, okay. So we have 7 bits here and we want to write the answer in 8-bit register. So what we will do, we will add 0 on my left hand side, okay. And then I will write all these remainders over here, okay, starting from my left to right, okay. So this is the way I will be filling my this 8-bit register, right. Now the next number is minus 93, okay. Now this is very important. You need to write the answer for negative 93, not for positive negative not for positive 93. So what you have to do, just for a moment, ignore the negative sign and first consider only 93, okay, the positive 93, and you need to write down the answer in binary code, okay. So I just told you how you will convert into binary. Similarly, you can convert this 93 using this method or this direct method of using powers, and you will get the answer for this 93, okay. Once you get the answer for positive 93, you have to convert it into one's complement. One's complement, you have to convert the value of 1 into 0 and 0 into 1, okay. So you have to invert all the values. So you, in the blue color, you can see I have converted all the values into in their equivalents one's complement. And then for converting them into 2's complement, you have to add 1 in your least significant bit on your right hand side. Over here I have added 1, so 1 plus 0 is 1. Okay, and the last bit, they are not adding up with any number, so you will just rewrite these bits over here. Okay, so this is my final answer for negative 93, so I can write it here in the 8-bit register, right? Okay, the next question is, using 2's complement, show how the following Danny number could be stored in 8-bit register. Again, 8-bit register, and you have to use 2's complement. So this is very simple. Again, the same method, 124 can be written by using direct method, by using these powers, and you have to think about how many numbers I have to add from these powers so that I can get 124. So I just wrote down these powers over here, and when I add 64 plus 32 plus 16 plus 8 plus 4, I will get 124. And the second method is that you can do like this, the division over like this, and just write down the remainder in this direction over here, right? Okay, now the next question is minus 77. So again, for minus 77, I will tell you the second method, so how you can get the answer without using the long method over here, like converting it into 1's complement and then adding 1 and getting the 2's complement. So what you can do, you can apply the this method of using the powers over here, but one thing will be different, that for negative number, the last bit will be having a negative power. Okay, so this will be 1 2 4 8 16 32 64, but the last bit will be having the power of minus 128. Okay, so if you will add this number, so now if you have to think that which numbers I have to add up to get minus 77. So this is minus 128, minus 128 plus 32 plus 16 plus 2 plus 1, you will get minus 77. Okay, or either you can use this long method, right? Okay, for the next question, what you have to do, you have to convert the two number in part A into hexadecimal. Okay, so I have this 124 and minus 77. My 124 is positive number. Okay, so how you can convert into the hexadecimal? Okay, for the next question, what you have to do, you have to convert 124 and minus 77 into its equivalent hexadecimal. Now, this is positive number and this is negative number. For positive number, how you can convert into hexadecimal is that simple. You have to divide this number, whatever number is given to you here, 124. You have to convert into hexadecimal. So, we will divide it with 16. Why? Because hexadecimal base is 16. We have total 16 numbers in hexadecimal, starting from 0 till 9 and then from A till F. So total we have 16 numbers in hexadecimal, so we will divide it with 16. So 16 times 7 is 112, and I will get the remainder of 12. Okay, so this is not further divisible by 16 because 7 is smaller than 16. So I got 7 and 12. So for hexadecimal, I have to write its equivalent code for any number that is greater than 9. So the code for 12 is C. Okay, so I will be writing here 7C. Now the next number is minus 77. Okay, now listen carefully, this is negative number. So if you have a negative number, you cannot directly divide it with 16. Okay, because when you are dividing here any number, that is a positive number, you need to convert the number that is in that is a negative number. So for that, what you have to do, you have to do these two steps that I'm doing here. Okay, first of all, just consider 77, right? Okay, and then divide it with 2. Okay, and then you keep on dividing. 2 times 38 and I will get the remainder 1. Okay, 2 times 19, I will get remainder 0. Okay, then 2 times 2 nines are 18 and I will get remainder 1. Okay, and then 2 times 4, remainder is 1. 2 times 2, remainder is 0. Okay, and 2 times 1, remainder is 0. Okay, so what I got, 1 double 0 double 1 0 1, and how many bits are there? 1 2 3 4 5 6 7. So I will need to make it 8 bits. So what I will do, I will add 0 on my left hand side, and then I will write this answer over here, and similarly in this direction. Okay, including this 1 also. So my answer will be 1 double 0 1 1 0 and 1. Okay, this is 0 by the way. Okay, now what you have to do, you have to convert into its ones complement first. Okay, so it will be 0 1 0 0 1 1 0 and 1, and then you have to convert into 2's complement because you're dealing with negative number. Okay, so just add 1 over here, so I will get 1 1 0 0 double 1 0 and 1. Okay, now you got the answer for, yeah, you got the answer for negative 77. Okay, so this is negative 77 into its equivalent binary number, right? So once you get this, what you have to do, you have to write down its equivalent hexadecimal. So for hexadecimal, what you can do, you can make a group of 4 over here and a group of 4, and then just add up the powers for the numbers or bits that have value of 1. So this is 1 and this is having the power of 1 and 2. Okay, so 2 plus 1, we will have answer 3. Okay, so what is the power over here? 1 2 4 and 8. Okay, so 8 plus 2 plus 1. Okay, so what I will get? 11. So for 11 I can write B, right? So my answer will be B3. Okay, now there's another method that you can directly use instead of using this long method, that you have to think of what is equivalent to minus 77 in term of these powers. Okay, so we already got this answer, minus 77. Okay, so what you can do, just simply you could have make group of 4 over here like this and this. Okay, and the answer you will get is B3, right? Okay, the next question is you have to write the equivalent number for BCD 359 into its BCD form, right? So what you have to do, you have to treat every digit individually. 3 is a separate digit, 5 is a separate, and 9 is a separate, and you have to write their equivalent binary code. Okay, and then you have to write, okay, in the next question you have to write the number 359 in BCD form. Okay, so to write in BCD form, you have to write the equivalent 4-bit code into its binary digit. So for 3 we have a 4-bit code. For 3 is 1100. Okay, why? Because if you add up the power 1248, you will get 111 over here and 00 over here. Okay, for 5, if you add 1248, you will get this equivalent code, and for 9 similarly you will get 1001. Just for recap, I can write the powers over here so you can recall how you added the power 1 2 4 and 8. Okay, so 8 plus 1 equals to 9. Similarly, you can use this power over here to see what makes the 5 and what makes the 3, right? Now next is describe a use of BCD number representation. So basically the binary coded decimal, they are used when binary number need to be represented electronically coded, and also decimal fraction can be accurately represented using BCD. Okay, next question is very important. The image is scanned with an image resolution 1024 multiplied by 512 pixel. These are the pixel. Pixel means the image height and width is given. Okay, and the second thing that is given is the color depth of 8-bit per pixel. What is the color depth here? 8-bit. You need to calculate the file size and you have to write the answer in maybe bytes. Okay, so for whenever this kind of question comes, remember you have to use this formula. The image size is equals to number of pixels, whatever is given in here in terms of width and height. You have to multiply them with the bit depth or color depth. Okay, bit depth or color depth, you have to multiply it with the number of pixels. So number of pixels were 1024 multiplied by 512, and what is the color depth over here? Multiply by 8. So I will multiply it with this. Okay, so whatever answer I will get, it will be in bits. Okay, because I have color depth of 8 bits per pixel. So after multiplication till here, till this part, I will get the answer in bits. So I have to move forward and convert it into maybe bytes. So before converting into maybe byte, I need to convert into bytes. From bits I will shift toward the bytes. So because 1 byte equals to 8 bits. So whenever you are converting bits into bytes, now you are moving from smaller unit to a bigger unit. So remember, you have to divide it. Okay, divide it with 8. Why 8? Because 1 byte equals to 8 bits. So after dividing with 8, I will get answer into equivalent bytes. Okay, so this will be cancelled, 8 will be cancelled by 8, so a final answer I will get is 524288. Okay, now whatever answer I got is in bytes, so I need answer in maybe bytes. So what I will do, I will divide it further with 1024 by 1024. Why? Now you need to memorize this table in the same order. If you will memorize the same order, it will be easy for you to do these conversions. Okay, so remember, what 8 bit equals to 1 byte, so you have to move this out: bit, then byte, then kb byte, then mb byte, then gb byte, then tb byte. Okay, so if you want to move from bytes to kibibytes, okay, if it would have asked you to just write down answer in kibibyte instead of megabyte, so you will have just to divide it 1024 only one time. Okay, why? Because 1 KB byte equals to 1024 bytes. But they're asking you to, to move from KB byte to megabyte. Okay, even move further. So you have to divide it 1024 multiplied by 1024, because to reach from byte to KB byte, you have to multiply, you have to divide with 1024 one time, and again to convert from KB byte to megabyte, you have to again jump one time more, 1024 times. You have to multiply it 1024 multiplied by 1024 and divide it with the byte. Okay, so final answer you will get is 0.5, right? Okay, in the next question, what you have to do, there's a table given over here with the letters name, address, and the memory contents. So what you have to do, give the hexadecimal value of memory contents for you. Okay, this is the binary value over written over here, and you have to convert into hexadecimal. So remember what we discussed earlier, that you have to divide them into group of 4. Okay, this is group of 4, second group, and this is the third group. Okay, so then what you have to do, just I'm writing this one here, 0 0 1 1. Okay, then you can give the power of 1 2 4 and 8. Okay, so what you have to do, you have to only add the numbers with 1 bit. Okay, so ignore the zeros. 8 plus 4 is 12. Okay, 8 plus 4 is 12, and you have to write the answer in hexadecimal. So in hexadecimal, we don't write 12. What we write, the equivalent code starting from A. So for 12, we have equivalent code is C. Okay, so for this value, the answer will be C, and for the next group, 0110. If you use the same formula over here for 0110, what you have added, you have added 4 and 2. Okay, the rest of the bits are 0, so you don't need to add. So what you get, 4 plus 2 is 6. Okay, so what answer you will get here? 6. Okay, for the next group, 0010, so this is 1, this is 2, and this has a power of 4, so only we are adding 4, so I will get the answer 4, 6, and C. This is my hexadecimal value. So next question, you have to convert the binary denary number 40 into its equivalent binary. Okay, so remember this formula where I ask you to use the powers. So how I can get 40? Okay, so just add up different values by using these powers. So if I add 32 and 8, so I will get 40. Okay, so the rest of the bits will be 0. So for 8-bit register, what I can do is that I can write the answer in this way, that my answer will be 1 0 1 triple 0. Okay, so when I write this with the power, it will 1, 2, 4, 8, 16, and 32. And you can read in the question, they have not specified that you have to represent it using 8-bit register. So whenever I get the 40 by adding this different bits, I will stop there. I no need to add further 0 over here on the left hand side to make it 8-bit. Okay, so just remember 40 is equal to 101 triple 0, right? Okay, Now next question is, bitmap graphics are used to represent squares S, T, and U. These can be saved in number of different image resolution. Give the number of bits required to store each pixel for black and white bitmap. Okay, so one over here is the number of bits. So if I use this formula 2 raised to power n, and I write 2 raised to power for n, I write 1, so I will get the answer 2, which gives me the total number of colors that are being used, black and white. So you have to think logically. So what should be the power of 2 so that I can get these two colors? Okay, so if in the question they ask you that you are using four colors, suppose for you are being given that you have to use four colors, okay, and then you have to determine the number of bits. So you have to use 2 raised to power n formula, and how many colors you get? 4. Okay, so what should be the power? It should be 2 raised to power 2. Okay, so this 2 will be the number of bits that will be required. Okay, so I have to estimate that what should be my power so that I get these number of colors. If they are asking 4 colors, so I will use 2 raised to power 2 so that I can get 4 colors. If they are asking these 2 colors, so I will be using 2 raised to power 1 so that I get the total number of color equals to 2. Okay, so how many bits I have used this power for n? I will be using how many? 1 bit. Okay, so my answer will be 1 bit. Okay, the next question is, these can be saved in a number of different image resolution. Give the number of bits required to store each pixel for black and white bitmap. Give the number of bits. Okay. So how many bits are required to store each pixel for? We just solve this. This is equivalent to, I will write here, 1. Okay. Now identify how many bits are required to store each pixel for 256 color bitmap. Okay, so again you can apply the same formula. Remember this 2 raised to power n equals to, you will get whatever is the answer is number of colors. Okay, number of colors. Okay, so you have to think that what should be the power of 2, or what should I replace by n so that I get 256 color. So if I start from 1, 2 raised to power 1 is 2, 2 raised to power 2 is 4, 2 raised to power 3 is 8. Okay, so keep on going, and if I write here 2 raised to power 8, okay, so the answer I will get is 2 raised to power 8 is 256. Okay, so how many bits are required? 8 bits. How many bits? 8 bits. Okay, I hope this is clear. So you can say that each color is represented by one of the 256 values, right? How? Because 2 raised to power 8 equals to 256. So when you are explaining, you can write this point over here. This point also over here. Okay, next question is, the following information refer to a music track being recorded on CD. Music is sampled 44,100 times per second. Each sample is 16 bit. Each track requires sampling from left and right speaker. Calculate the number of bytes required to store 1 second of sample music, showing your working. Okay. Okay, so what we can do, we can use this formula which we already discussed. This was to estimate the file size. Okay, so again they're also asking you to calculate the number of byte that will be actually the file size or image size. So what you can do, in the last question we saw that we were multiplying the number of pixel with the bit depth. Okay, so what here you can do that whatever the sample is given to use, music is sample 44,100 times per second. Whatever data is given to you, you have to multiply that data 44,100 with with the bit depth. Each sample is 16 bit. This is the bit depth, so you have to multiply with 16. Okay, the next is each track requires sampling for left and right speaker. This means that you have two channels available over here for each track. So if these kind of data is available, so you have to multiply with 2. Why? Because you have left and right speakers, so there are two channels, so you have to multiply with 2, and then whatever answer you will get, it will be in bits. Okay, because you have sample of 16 bits, so answer will be in bits. So what is required, you have to convert the answer into bytes. Okay, so for converted into bytes, we will divide this whole upper portion with 8. Track 4 minutes, and you have to convert into seconds, so you need to multiply into 60. Why? Because 1 minute equals to 60 seconds. So I'm multiplying this 4 with 60, and then I will multiply it with the above answer that was in bytes. 17, that was the size of the the music sample in bytes. 176400. Okay, and then what I have to do, whatever answer I will get will be in byte per second, so I have to convert in megabytes, right? So for convert it into megabyte, from byte to megabyte, I will multiply 1024 multiply by 1024. Okay, and I'm dividing with the upper part. Okay, so the answer. Okay, the next part is when storing music track in a computer, the MP3 format is often used. This reduces file size by about 90%. Explain how the music quality is apparently retained. Okay, so what the format is? MP3 format. Okay, basically you are storing the music in audio form. Okay, and they're saying that after applying a certain compression, it will reduce the size of the file to 90%. And still, after reducing, how we can retain the music quality? So I just go back to this portion of your chapter where it was written that if you reduce any file size by 90%, so you are reducing something. Okay, something is being lost from that music. So it means that what kind of compression you are using? You are using lossy compression. Okay, because when you are using lossy compression and still it is retaining the music quality, it means that you are using perceptual music shaping. What is perceptual music shaping? Is that first you need to understand that the human ear is capable of listening 20 hertz to 20,000 hertz. Okay, only this sound. So any sound that is below this range or above this range is not audible. You cannot understand what is being said, right? So in the perceptual music, what is being done, that any sound that is outside the range of this frequency, we just ignore that, right? And if two songs are played at the same time, only the louder one can be heard by the ear, so the softer sound is eliminated, right? So this answer you are going to write down in this part, that first you will be using lossy compression, then you can use the perceptual music shaping to reduce the noise, and then we can use the frequency that are outside the human ear, and eliminating the sound that is softer tone, and only including the sound that is louder, right? And the next question is black and white image is 512 pixel by 256 pixel. Calculate the file size in KB, right? Okay, we have already done this part above where we explain the black and white image. Okay, now you need to see this question, that in this question they have not given you any color depth or bit depth, right? They have only given you the height and weight or resolution of the image. This is in pixels. So to move forward, you need to convert this pixel into either bits or bytes or kilobytes, right? You to estimate the file size. But if you multiply 512 by 256 and there is no bit depth or bit color depth given, so how you will reach this answer? By converting pixel into bits. So remember that for this question, you should remember that black and white, for the black and white color, each pixel requires 1 bit. How many bits? For black and white color, each pixel requires 1 bit, right? So what you can do, that simple, you can use this formula that sir I will get will be in bits, right? So after getting this, I will be converting this bit into bytes. Okay, so what I can do is that I can divide the whole answer with 8. Why I'm dividing with 8? Because this, after this multiplication, I will get the answer in bit. Now I need to convert into byte. So 1 byte equals to 8 bits. So that's why I'm dividing it with 8. Okay. So once I divide with this, I will get 16384, right? Now this answer will be in bytes. Okay. So I need to convert the answer into kilobytes. So we know that 1 kilobyte equals to 1024 bytes. So we will divide this 16384 by 1024, right? And I will get 16 kilobyte, right? This is my answer. Okay, in the next question you have to tell that what is our run length encoding and how do we do that. Okay, so basically I will go back to your book. Okay, let's take this example. In this example you can see there is a string a b b b b c c d d d d d. Okay, so when you're storing this kind of string that has adjacent a's and b's and c and d, how many bytes you are using? If one character is using 1 byte, so total we need 16 bytes to store that, right? And for each adjacent character that is repeating itself, you will count how many time it is repeating, and then you will write that count, and after that you will write its equivalent code in ASCII. Okay, the equivalent code of a in ASCII is 97. So instead of writing this, we can write its count equals to 5 and the code for a is 97. Similarly for b, we can count how many b's were there, 4, and the code is 98. And similarly we can do for c and d. Now see, the first row will be using 16 bytes to represent this string. Okay, whereas if I use a run length encoding, what will be used? I will only be using 8 bytes. Assume that you required 1 byte to store each number. Okay, so 1 byte, 1 byte, 1 byte. So I will be requiring 8 bytes for storing this data, and I will be requiring 16 bytes to store this data. So when you are using run length encoding, this is basically lossless compression, which is you can say a reversible file. So what it is doing, it is reducing the physical size of all these adjacent string or characters by repeating the string into two values by count and their respected code value, right? So in this way you can reduce the storage amount that is being used by the string or number of characters used. So this is basically run length encoding. So we will go back to the question. So I hope I explained what is run length encoding. And now you can see a table where you have been given the color symbol P and W and their equivalent code. So you have to write down that how you can write this code into its equivalent run length encoding, right? So how basically it is compressed, you have to write for row 1, row 2 and row 3. You can see there are 3 rows, and this the last one is empty. We just need to write the answer for row 1 and 2 and 3. So first, I told you first step is that count how many b's are there. 1 2 3 4 5 6 7 8 9 10. There are 10 b's. Okay, so what I can write 10. And what is the equivalent code for b? We can see from this table it is 153. Okay, so this is basically for row 1. I have 10 and 153. Then what is next? White, how many white? 3. So I will write 3. And then what is the code for 3? 255, right? So in this way I will keep on writing. Let me drag it. Okay, after 3 255, count the number of blacks again. Okay, so now how many black are there? 1 2 3. Okay, again 3. And what is the code for black? 153, right? Now again for row number 2, Okay, row number 2, how many blacks? There are 9 blacks. Okay, so I can write 9. Sorry, I can write here 9, and the code for black is 153. Again, count how many white? 1 2 3 4 5 6. Okay, so I will write, or you can also write, okay, 6, and the code for white is 255. Okay, and then how many blacks? We have 1 black, and what's the code for black? 153. Okay, for row 3, how many blacks I have? I have 6 black, so I will write their count and I will write their code. Okay, and then how many whites I have? I have 9 black, and their equivalent code is 255. Okay, you can also write it, you can write the code first and then the count, or you can write the count first and then the code. Both are correct. Okay, there can be another alternative solution for this, for row 1, row 2 and row 3. Now see, when I counted the number of black in the first row, I have started my count from 1. Okay, so 1 till here, over here I have total number of blacks are 10. Okay, but if I see they have given the numberings over here 0 1 2 3 4. So if I start with this numbering, so how many bees I will get? I will get 9. Okay, so alternative is that for row 1, what you can do is you can write 153, its equivalent code first, or then value b will be 9. Okay, and then 255, the code for white, and how many values? There are 3 values, but because we are writing, we are considering the numbering from 0, so I will write here 2. Okay, then 153 and 2 for black. Similarly for row 2, I will be using 153 and 8 blacks, then 255 and 5 white, then 153 and 0 for black. Okay, then for row 3, I will be using 153, the code for black, and how many black? 6, starting from 0. Okay, so there will be 6. Okay, then 255 and how many white? 8, starting from 0. Okay, so this can be my alternate solution, right? I hope I am clear.